Hello, we are Group 8 and we're going to talk about cloud automation, CI/CD, and canary deployment. The paper we chose were a model-driven approach to continuous practices, a comparison of different CI/CD tools integrated with cloud platform, and Docker container security in cloud computing.
Okay, so this paper talks about how continuous software engineering has become more and more popular over the years, but its implementation it's not easy to do, and uh, it seems to have to people that are not in the area more costs than advantages. So they present a model-driven approach that allows domain experts to model the processes involved in CSE visually by means of a dedicated domain-specific graphical language. This language has IDEA support and it's much easier to learn than the ones that are right now in the market. They talk about CI, CDE, and CD, where CI improves the quality of the software development. CDE ensures that the changes made are ready for deployment. And CD basically decouples the deployment, the business team, where they can deploy the whole app without being limited by technical issues. So basically, the modern web apps are made of one normal component and have some different things than the normal apps that aren't based in the cloud. As such, this model has to be aware of those different things. The normal CI/CD, they basically use the GitLab example, where it is based on a YAML file and configures a set of jobs that define tasks. These tasks execute some commands that do the CI of the app. Even though this happens, there's still some order that needs to be respected because, as an example, an app must be deployed before it can be tested or built. Taking from this GitLab CI/CD example, they say that it works, but there are some issues like the little support for reusage, the fact that the YAML syntax is too general to check if there is something wrong, and many others. So basically, to develop the language and the IDE, they use the meta modeling framework 5 that allows for the development of domain specific languages and their IDEs in a cheap and quick fashion. It also allows for the usage of limitations that help, for example, the developer to only build files that work. For the models, they talk about how the pipeline is modeled in a automatically fashion, as in it isn't written but it is generated, which allows for an avoidance of normal errors. There's also the pipeline versus the user mindset, where in the pipeline they think about how less is more, and in the user they think about how they can help the user understand better. As said before, in the GitLab example, the order is very important. And this model also says that there are some elements that define an event and the desired outcome. And these are the basic elements of this model. As a final review, they say that this modeling allows for some main advantages over the normal tools that are now used, like the reusage of jobs that can be parameterized and then reused in various contexts. The syntax of the pipeline is guaranteed, as in it won't have any type of errors because it is not written, it is built. With the last two advantages, the configuration becomes much easier and overcomes the most typical errors. And the complexity is also reduced, as in it becomes simpler and a lot easier to read. As a final note, they say that the versatility of the language is very high and there are many paths it can take.
Okay, so now let's talk about the comparison of two different CI/CD tools. So first, why do we need these tools? So in a project, It starts with a small number of microservices, but then as we add more functions and more functionalities, that number of microservices increases a lot. So it becomes really complicated to do a manual management and deployment of these services. So we use continuous integration and continuous delivery. Continuous integration, also known as CI, is a practice that establishes that there is a common repository that stores the code, and when a change is submitted to that code, it's automatically integrated to the rest of the code and the rest of the system. But before it passes a number of tests. So in this practice, short-lived branches with small functionalities are preferred to avoid the number of conflicts that can happen. Continuous delivery. Continuous delivery happens after a successful CI, and a script picks up the code, prepares the build, and deploys it to an environment, either a test environment or a production environment. So this paper contributes with three things. First, it creates a setup where you can compare and observe the performance of Jenkins versus GitLab. That are the two tools we are going to compare. Then it proceeds with the comparison of the performance of the deployment and build creation time. And finally, it analyzes this performance and can conclude for which type of projects these tools are better for. So first, Jenkins. Jenkins is a Java-based CI/CD tool. It's very beginner friendly with a graphical interface and easy to install, and can be configured using different plugins. To access the repository where the code is stored, it needs a webhook URL. So the Jenkins deployment, it goes in 4 steps. First, a developer commits a new change, and this webhook is called. Then the Jenkins pulls the code from the repository and prepares a Java archive. Then, if the build is successful, the Docker image is created and the build is pushed. If there is any type of error, the developers are warned via email. Finally, a Docker image is created based on Docker file, and the image is pushed and deployed. In GitLab CI/CD, GitLab CI/CD is a web-based application that is based on Git, so it does not need any web URL for the hook. Its configuration is done via the pipeline. There are no plugins, and it can be executed by 3 runners: a share runner that is a single runner for all the projects, a private runner that is a runner for each project that needs to be configured for that project, and a group runner that is a share runner but for a small group, small number of projects. So the deployment in GitLab, it's similar, but there are some different things. So the new change is committed, the pipeline is triggered with again without the URL webhook. Then the pipeline triggers the runner to make a build. Can be a share runner, a group runner, or a private runner. Then the build is prepared and tested. And finally, the Docker image is created and is pushed. We can see that the last step, it's the same as in Jenkins. But there are some differences. I talk about the webhook that GitLab does not require. The server configured before build is in the case of a Jenkins and a GitLab. And we can see in the next slide that there will be some performance differences due to this. Jenkins will also be harder to manage in big projects before, as we install more plugins to do our configuration, those plugins can become really hard to manage. as in GitLab, we really only have the pipeline, that is a YAML file that can be configured, and we don't need to use different components and different plugins. So the private runner also configures the build before pushing it, whereas the share runner allocates the machine in real time. So the performance comparison, finally. We can see that in the GitLab share runner, these are all numbers for the average deployment time. We can see that in the GitLab shared runner, as he needs to allocate the machine in real time, it takes around 400 seconds. Whereas in the GitLab private runner and Jenkins, it takes almost the same time, 9 seconds. So we can see that GitLab share runner is also the default that GitLab uses, but we can configure the private runner and we can achieve the same performance for as Jenkins. So conclusions. We can conclude that shared runner, although it's the default, it's not the best when compared to the other runners we have. So Jenkins will be better for large enterprise projects, and GitLab will be better for small and simple ones.
So now we're going to talk about security in these components. Containers today have gained significant traction with the development community because it has some benefits using them, like the time. It avoids the time-consuming tasks of the configuration of libraries and dependencies for the code you are building. We can do multi-containers, that is running various containers inside the virtual or physical machine, so it's more efficient. And we can incorporate it on Docker, that is a tool that can scale containers. But there are some downsides to the use of this tool, like the malware. Today you can use microservices that are containers publicly available, and you can use them for your project, but you don't know if they are malicious or trying to do something malicious to your project or not. The current methods of analyzing these containers, they are time consuming, so it's not feasible for a project doing that type of scan. And the scan that are available, they don't scan for vulnerabilities in runtime, just do a static analysis. So the contribution from the authors with this paper are building a continuous integration and deployment pipeline to evaluate the Docker images and the security of them, the publicly available ones, and passing or not on the tests, and a dynamic analysis on those Docker images that we saw that didn't happen. So proposed on the CI/CD workflow an arbitrary number of stages with vulnerability scans from layer to layer, and depending on the number of vulnerabilities found in each layer, they pass or fail that test. They are published to the Docker registry when they pass all the layers of that test. The dynamic analysis is made by an API that automates and captures usable information, like using Claire operative system, that is a vulnerability analysis, a database to have the signatures of malicious content, an antivirus like Virus Total for scanning malicious content, and doing a dynamic analysis to detect malicious behavior. So the implementation and the implementation of the CI/CD architecture it was made on Amazon Web Services. They first created a virtual private cloud for isolating the various resources from the Amazon ecosystem. Then they isolated core operating system Claire and Anchor Engine in each availability zone, and each one has a public subnet and a private subnet. The Postgres SQL spawns the private subnets, and the source content of the Docker it's stored in the Amazon Web Service code commit repository, and whenever the code is changed, it's trigger the CI/CD pipeline, all the things we talked earlier. Dynamic analysis, it uses an antivirus such as VirusTotal, as we talk about. The downside of using an antivirus on the dynamic analysis is that most of them only perform static analysis of, if I can perform static analysis and look for specific signatures. In order to capture the traffic when the application is running, another container is run alongside with TCP dump that analyze the network traffic, but the TCP dump takes a bit to start, so the initial traffic from the target container may be lost, and in that traffic may be malicious content, and we can't capture it. We can also use the option from Docker that is log file systems, which can be useful to analyze if malicious images download or execute binaries that are not part of the original image. So the evaluation that we did, they used two projects, Nginx website with HTTP and HTTPS protocol, and a Postgres SQL database. As you can see from Claire vulnerability scan results, it did not detect any vulnerabilities on the second project, on the Postgres one, but on the Nginx website, there were a total of 143 vulnerabilities, but it still passed the test because the number of vulnerabilities from each category, the negligible, low, medium, and high, didn't reach any threshold, and the total sum of the vulnerabilities didn't reach any threshold either. So it passed the test. Come back. The VirusTotal scan results. We can see that it detected positive signatures on two packages. So the website wasn't published because of that. So, and evaluation from the dynamic analysis. The vulnerabilities detected are some, like file modifications and running process, and DNS queries. But what are those? First, that package writes two scripts on the on the root folder. So we can see that is some kind of malicious behavior. Then it also surveys the system and saves information such as the CPU metadata, and performs some IP searches and scan using Shodan, that is a search engine for the devices. Then we saw that it started to do SSH and Tor daemons connections, and it tries to authenticate with the Shodan to perform address searches to find open ports on the machine. Then the DNS queries are from the machine to a site that is on the screen, probably to mining cryptocurrency. So as we can see, that image didn't pass the evaluation and was not posted either. This static has some limitations, like the threshold we talked earlier. A random number of vulnerabilities is not good enough for production level security requirements. We can say that 150 vulnerabilities is the threshold, and anything lower than that pass the test. We can say from random numbers. We have to have specific numbers for each project. The anchor engine used on the dynamic analysis, the default security policy of it, may not define the security requirements that are in place in real world scenario by an organization. This tool can't also analyze custom image, just publicly available ones. So if you are doing a container, you can't analyze it. They didn't put this feature because the programmer or the developer at start knows that the package that they are using are trustful, but sometimes the trustful packages can be jeopardized and have some security vulnerabilities, and it can jeopardize the container too. So they in future implementations, they thought to implement a custom image scan. Any questions?